Heat treatment is the process of heating and cooling metals, using specific predetermined methods to obtain desired properties. There are various reasons for carrying out heat treatment. Some procedures make the metal soft, while others increase hardness. They may also affect the electrical and heat conductivity of these materials. Some heat treatment methods relieve stresses induced in earlier cold working processes. Others develop desirable chemical properties to metals. Choosing the perfect method really comes down to the type of metal and the required properties. In some cases, a metal part may go through several heat treatment procedures. For instance, some superalloys used in the aircraft manufacturing industry may undergo up to 6 different heat treating steps to optimize them for the application. Common types of heat treating methods include annealing, hardening, quenching, and stress relieving, each of which has its own unique process to produce different results. Annealing. Annealing is a heat treatment process used to modify the microstructure of a metal to improve its ductility while reducing internal stress and overall hardness. This allows the material to be more easily shaped without cracking. This process is particularly useful for steels, which can be too hard or brittle for forming processes. The annealing process involves heating metal to a temperature at which the crystalline structure becomes fluid, but the metal remains in a solid form. The metal is held at this temperature, which allows for any defects in the material to repair themselves. The metal is then allowed to cool back to room temperature at a slow pace to produce a more ductile crystalline structure. Hardening. Hardening heat treatments are used to enhance the hardness of the metal's surface through heating and rapid cooling. The material is heated in a hardening furnace to a temperature that transforms its internal structure without melting it. The metal is then held at this temperature for 1 hour for every inch of thickness, followed by rapid cooling. The quick cooling process establishes a harder, more stable crystalline structure. Flame hardening gear teeth. In order for all these processes to work properly, a complete flame hardening system is required. The proper flame head design, PLC controls of scanning speeds and heat times, control and monitoring of oxygen and fuel flows are critical for the proper flame hardening of steel gears. Laser hardening is a heat-treating process using high-power diode lasers to improve strength and durability of defined surface areas. Unlike other processes, the laser can be very selective, hardening only targeted areas of steel and cast iron metals. Very little or no distortion saves the user from expending too much effort in terms of reworking, reducing costs by up to 25% for these kinds of applications. Hardening with high-power diode lasers has the decisive advantage of enabling heat to be provided in specific stressed areas exclusively. For complex components, this enables parts to be hardened, while, in other zones, the ductility of the initial structure can be maintained. This localized treatment is not possible in many cases with induction hardening, which thus has disadvantages compared to laser hardening. As the workpiece is only heated near the surface with a low hardening depth in laser brazing, the heat is therefore discharged very efficiently over the neighboring material. Thus, there is no need for an additional quenching media in most cases, which keeps costs low. As the warpage is rather minimal compared to other hardening techniques, there is generally no need for additional methods to correct the material deformations. Quenching. Quenching refers specifically to heat treatments that rely on rapid cooling of the metal to achieve the desired physical or mechanical properties. Heated materials are often cooled in oil, but can also be quenched using air, water, and brine, depending on the material and desired qualities. As with other heat treating processes, the metal is heated to a point below the melting point where the crystalline structure is fluid. It is held for a specific period of time, depending on the desired properties, and then quenched in one of the above-mentioned media to reduce the temperature of the material and establish the required internal structure. Jayam Hyat Du Qua Vat Lu Va Thiat Lap Ka Truck Ben Trong Kan Thiat. Stress relieving. Stress relieving processes involve heating the material above the point where the internal structure transforms and then air cooling it at a particular rate. This process allows the structure to become more stable, reducing internal stress and enhancing the strength and hardness of the metal. It is particularly useful for metals that have been subject to stress-inducing forming processes, such as machining, straightening, and rolling. Induction heat treatment is a process of heating electrically conductive materials, such as metals, by electromagnetic induction, through a coil that creates an electromagnetic field within the coil to heat up the metal. Induction heat treatment can harden, soften, or anneal metals by changing their microstructure or surface chemistry. Some advantages of induction heat treatment are: it allows targeted heating of specific metal areas without affecting the rest of the part. It is fast, precise, and energy efficient, as the heat is generated inside the metal itself. It can prevent oxidation and decarburization of the metal's surface by using a controlled or protective atmosphere. It can control the hardness, depth, and pattern of the heat-treated zone by adjusting the frequency, power, and duration of the current. Some applications of induction heat treatment are: induction hardening, heating the metal above its critical temperature and then quenching it rapidly to form a hard martensitic layer on the surface. This improves the wear resistance and fatigue strength of the metal. Induction annealing, heating the metal below its critical temperature and then cooling it slowly to reduce its hardness and increase its ductility. This improves the workability and machinability of the metal. Induction tempering, heating the metal below its lower critical temperature after induction hardening reduces its brittleness and increases its toughness. This improves the impact resistance and elasticity of the metal. Vacuum heat treatment. Gears and shafts are usually hardened through heat treatment to resist wear and dents. The first production process required for all parts is a pre-wash operation. This process is required to remove all remaining oils or contaminants on the part surface as well as loose chips or burrs which may damage the heat treat equipment. A mild cleaning solution is used with warm deionized water to cut the oil and rust inhibitors included to prevent any rust formation. A clean surface is required for the heat treat process as any oil or contaminant can effectively mask any surface carburation applied during the process. ALD manufactured module therm heat treat system is a technological marvel. It connects up to 12 independent vacuum treatment chambers with the transfer and external cleanse chamber. That moves on a rail system. The equipment is extremely flexible because it allows many different processes to be active at the same time. The material or workpiece to be treated is heated to a suitable temperature by induction in a vacuum and kept at a high temperature for a certain period of time, and then cooled down with liquid nitrogen to as low as -300 degrees Fahrenheit, so as to change the surface hardness and wear resistance. All products require a post-wash process to apply a rust inhibitor that minimizes the likelihood of rust during transport and storage. The ion nitriding process is carried out in a vacuum vessel where a high-voltage electrical charge forms plasma, causing nitrogen ions to accelerate and impinge on the metal. When the nitrogen ions bombard the part, they heat up the metal, clean the surface, and absorb nitrogen into the surface. This process is sometimes referred to as ion nitrocarburizing or plasma ferritic nitrocarburizing, FNC. Plasma nitriding and Nitriding process is carried out in vacuum. High voltage is applied to the chamber which ignites the glow discharge. The first stage is cleansing. The parts are cleaned from any grease, oil, or dirt left. The pulsed plasma generator prevents the formation of arcs. The second stage is heating. Nitrogen ions bombard the surface of the components and their kinetic energy turns into heat. The heating speed is easily controlled. The third stage is the process. Nitrogen atoms diffuse in the surface of the components, forming the nitride layer. By controlling the main process parameters, temperature, pressure, gas mixture, and time, a nitride layer of your specific requirements is achieved. Benefits of ion nitriding. Extends part/tool life. Selective hardening process. Reusable masking versus coatings or other surface treatments. Adds performance, fatigue strength and endurance. Enhances surface lubricity. Minimal growth/distortion. Reduces erosion. Increases material flow in molds and dies. Cleans the part.